So in this part, we are going to learn vector functions. We know vector function, vector value function. So far, yeah, so we know what is scalar valued function, vector valued function. Now we are going to discuss, the file is not available. Yeah, I will upload this file to LMS download. Yeah, so yeah, scalar field. So the output of a scalar function is always a real number, right? Real number, right? So domain could be 2-dimensional, 3-dimensional, 4-dimensional, n dimension, right? But the output should be a real number. So a value, element in the real line, right? So this is an so normally scalar valued function so we use a lowercase letters or big letters to indicate scalar valued function here, simple lowercase f. But vector value, so how do you represent? Yeah, so we use uppercase with tilde, and f. Yep. To indicate vector fields. Yep. So look at the output here, output set. So this is real number set, but this is R3, Rn, like that, right? So R3 to R3. The output is also a vector, right? So the input also a vector and output also a vector, right? Input also a vector, output also a vector. So earlier, input is a vector, output is a scalar. Input is a vector, output is a scalar. So this time, input and output both are vectors, right? All right. So these are a couple of examples for vector valued functions. We already learned what vector valued function is. And if you, standard basis. So here we are using standard basis. So IJK standard basis, right? Standard. So if you draw the axes of x, so there are 3 axes, y and z. So if you select these, this is I, J is the unit vector along OY, otherwise K. So you can write any point in terms of X, Y, and Z. Standard, these are called standard basis, right? Or you can write in triple, how do you call it? Triple notation. Yep. So like this. Some people write like this, or like these brackets, or sometimes we use surround brackets, or you can use anything. So this is good, right? So can the domain and range be in different order in vector value function? Like, yes, it could be different. Yeah. So you can define. So let's define R3 to R2. So X, Y, Z vector is mapped to X, Y, comma, Z squared, like this. Don't know whether this is well defined. I just wrote. Yeah. So like this, this is a, so look at the dimension. Dimension is 3 and this is dimension is 2. Okay, can be defined. So maybe You can put a higher dimension, 10 or something. This is map to x 2x plus y, comma, comma, like this, right? Can define any function, but don't know whether this is well defined. If it is well defined, you can. Yeah, you can define. This could be different numbers. Could be these numbers be different. Not same 3 3. It could be 3 2 or any higher degree. Okay, that makes sense, right? All right. So here, if you want to refer to the individual component, three components. So this is x component. Yeah, you can denote. Don't. So here, so sometimes you get confused with this notation. So this is not the first derivative of f, right? This is the first x component of f, and y component of f, and z component. Right? You can visualize if you go to this link. Yeah, so let me yeah. So copy the link. Yeah, just yeah, I will to everybody. Yeah, so just go to this. So this is you can visualize this. Yeah, three-dimensional. Yeah, three-dimensional. PQ. Yeah, you can give any function values. That give me a second, right? Yes. So here, so this is domain. Yeah, domain is R2 because it has two components, x, y, right? And yeah, so let's draw outputs at these points. So let's consider, yeah, x1 is 1, y is 0. And what is the output when you plug this one into here? I plus, yeah, there is no, yes, j component. All right, yeah, at this point, what is the output? Yeah, in the direction, yeah, this is I direction, j, direction, yeah, this direction. I will draw in different color. Will use, yeah, this is the output. Okay, and if you draw this one, this point, this is 1, and let's say this is -1, and this is the point. We are considering, yeah, 1 1. So plug 1 into here, x is positive, 1, and -1 downside, and the resultant one is this, right? What is this one? Negative. Not into this, yeah, 0. There is no I component. This is the output. So like that, yeah, you can draw, or yeah, you can. Yeah, so these are the outputs. Yeah, outputs of this. So we use yeah, both. We use same axis to draw outputs, puts and outputs, right? So this is the input and this is the output. This arrow is the output, right? All right, makes sense. Yeah, if you consider this, yeah, three-dimensional one again. So function is defined in this way. R is same with, so let's rewrite this. C is a constant, R is your x, y, and z divided by, yeah, square root, x squared plus y squared plus z squared to the power 3 halves cos magnitude of r to the power 3. Yep, magnitude of r cube. Yeah, this one. Yeah, what is the magnitude of f? Yeah, so when you take the magnitude, yeah, let's take the magnitude. Yeah, magnitude of this one is square root of x squared plus, when you simplify this, yeah, you can simplify, yeah, when you simplify, yeah, you get 1 over r, right? C over, yeah, so magnitude of r, yeah, r squared, yes, yeah, this. Now, what is the magnitude x plus f in terms of x, y, and z? Yeah, you can do that. Yeah, like this. And what are the components? Yeah, x component x over this guy, y component y over this guy, z. Yep, yeah, easy. Yeah, you can draw the outputs at these points. Yeah, function outputs. Yeah. Yeah, yeah, another, yeah, let's use this to draw that vector field. What is the field? Minus y, yeah, x. So x component is minus y, minus y. The one is x, x. This is 0. This is because this is two-dimensional, two-dimensional, 0. Yep, so this is two-dimensional one. Here, look at this x and y. There is no z component. So, because there is two-dimensional, yeah, so you get something like this. Yeah, like, yeah, spiral. So, yeah, something like this. But how do you say this? So this is, how do you call this? Yeah, but, yeah, something like this. Turbulence at this point. Yep, like that you can draw, yeah, yeah, vector fields. So those are, yeah, so 2 dimensions or 3 dimensions, right? Yeah, you can use this online plotter to plot in vector field. You can visualize. So here there is no z component, right? So there is no height. So everything you get the same thing here. Yeah. So when you see the two-dimensional vertical, yeah, you get, yeah, this. Can you please upload this? Yeah, I will do this. Forgot to upload. There I had a class in the morning. Yeah. So other tool, yeah, this is very important. Divergence of a vector field. So let's consider a three-dimensional vector field. This is the first component, second y component, and z component, right? And the divergence is defined as follows. Here is the definition. So this is the notation: divergent gradient, divergent dotted with vector field. You take the dot product with this gradient operator and the field f. So gradient, you know the gradient operator, which is partial with respect to x, partial with respect to y, partial with respect to z. Yeah, this is the operator. You operate this one with vector. Yeah, how do you operate? You take the dot product. Take the dot product. Then we call this as the divergence of divergent of the vector field f, right? So you can expand this. So dot product, what is the x component? X component of f, x1. Started with this partial with respect to x, f, simple f1, and plus partial other one with respect to this one, f2, plus partial with respect to z, third one, f3. So this is the divergence of the vector field f, right? So what does this mean? Let's actually this is a scalar. So this is a scalar field. So you get a scalar field. So this is a scalar field. So this is not a vector. Always you get a scalar function, right? Scalar valued function, right? So that is the remark, right? So once if you have that product always give you a scalar, because f is a function here, of x, y, and z, then this is a scalar valued function, right? So here we have some relationship between x, y, and z here, right? For instance, how do you, so here, let's compute divergence of this, So this is the first component of f, second component of f, and the third component. So how do you compute the divergence? Take the dot product of gradient operator and f. This is a scalar. Partial with respect to x of the first component, x squared. So I wrote this down now. X squared minus z cube plus partial with respect to y, the second component, this component, and partial with respect to z, last component. So let's simplify. So when you differentiate this function with respect to x, this becomes 2x, other term becomes 0. 2x, we don't write zeros, right? When you differentiate this guy with respect to y, let's differentiate. 2x times 1, 2x times 1, I don't write 1, plus, when you differentiate this with respect to y, yeah, 2e to y. And the last one, partial of this with respect to z, partial of this, yeah, partial of this guy with respect to z, then this becomes 2z here. And other term, there is no z term. So when you partial differentiate this term with respect to z, this becomes 0. Yeah, so this is the divergence here, divergence of f. So which is a function of x, y, and z. Yeah. So this is a scalar function, right? Scale function, scalar value function. Okay. All right. Any questions? Any doubts? Any questions? Clear? Is that clear to you? Definition. This is the definition. So next one we will see. So we want to find the meaning of this. Meaning of the divergence. Why people use divergence of a vector value function? Why we compute this divergence? Yeah, let's see. So actually, if you have a field like this, field like this, let's say vector field. මන්දන්න සුලියට කියන්නේ ටර්බයින් වර්ද කියන්න මේක නිකන් සුලියක් වගේනේ මන්දන්න කොහොමද කියන්නේ නිකන් සුලියක් වගේ alright okay why people want to find this divergence of a vector field, right? So let's find so actually what does it mean? Why do we need this tool to analyze a vector field, right? So actually it gives you a measurement of a flux density of a vector field at a point, right? So for instance here, let's say if you have a divergence. So when you compute the divergence of a vector field at a certain point, let's say, at a certain point, for instance, so like this, and here you have a two-dimensional vector field. What is the equation of this? So this is the equation. All right. So let's compute the divergence of this vector field. Gradient dotted with S. So this is P is this one. All right, when you differentiate partially with respect to x, that is 0. You differentiate this q partially with respect to divergence is 0. What does it mean? So everywhere divergence is 0. That means the flux of the flow at a certain point, flux of the flow of this vector field. If you consider any point, let's say any point, right? Any point, the rate of the flow flowing into this point is same with the rate of this vector field flowing out. Both are the same. That's why you get 0, right? And you measure the flowing rate. So if you consider any point in the space, in this two-dimensional place, so 0 means so the rate at which the flow flows into this into this point is same with the rate at which the flow flows out from this, flows out from this point. So both are the same. So there is no flux actually at this point. So there is no flux at this point. So flowing in and flowing out are the same. Rates of flowing in is same with the rate of flowing out of this vector field. Got it? So that is the divergence. Yeah, that is the divergence. So if you want to, so if you have a positive, so here look at this. Here look at this. If the divergence of a vector field is equal to 0 at a point, the rate at which fluid is flowing into that point is equal to the rate at which fluid is flowing out. Flowing in, the rate of flowing in is same with the rate of flowing out. If you have a positive divergence, let's say, when you compute the divergence, then at a certain point, then you have positive divergence. If you have positive divergence at a certain point, that means, the fluid flowing out than flowing in. So that point acts as a sinkhole. කියන්නේ ඒක ඇතුළට යනවා ගොඩාක් නේද? positive divergence එකක් වුණොත් ඒ point එක divergence එක positive වුණොත් fluid එක ගොඩක් ඇතුළට යනවා එළියට යනවට වඩා. ඒ කියන්නේ මේක sinkhole එකක් වගේ sink එකක්. Got it? Did you understand? So positive divergence, specific point, more fluid flowing out. Out, not flowing in. ගොඩක් එළියට එනවා. ඕගාල එළියට එනවා. ඇතුළට යන එකට වඩා ගොඩක් එළියට එනවා. Flowing out than in. හරි? ඒ කියන්නේ positive divergence. Negative වුණොත්, if you have a negative divergence flowing in than out, other way around. If you have negative divergence at a certain point, flowing in, the rate of flowing in than flowing out, පොඩ්ඩයි out. මේක sinkhole එකක්, මේක නිකන් source එකක් වගේ, source එකක්. If you have positive divergence, this point acts as a source. If you have negative divergence, this point acts as a sink. If you have zero divergence, flowing in එකයි out දෙකම සමානයි. එහෙනම් මොකක්ද ඒක? Incompressible loss. Solenoid. ඒකට කියන ඒ වගේ වෙක්ටර් ෆීල්ඩ් එකකට හැමතැනම මේ වගේ zero වුණොත් මෙන්න මේක මොකක්ද ඒ වචනේ solenoidal. So this is an example of solenoidal vector field, because if you compute the divergence of this vector field at any point, you get zero. That means if you consider any point, the flowing in, the rate of flowing in is same with the rate of flowing out. කොහෙවත් sink එකක්වත් source එකක්වත් නැහැ. Bernoulli, මතක Bernoulli නෙමෙයි Doppler ආච්චිට නේ. source and මතකයි නේද ඒව නේ? flowing in මොකක්ද sinkhole එකක්වත් නැහැ. ඒ වගේම source එකක්වත් නැහැ. ගොඩක් එන තැනක්වත් වතුර උල්පත්වත් නැහැ. වතුර උල්පතක්වත් නැහැ. නිකන් ඇතුළට යන හිලක්වත් නැහැ මේකේ. එහෙනම් ටිකම යනවා එළියට අනිත් පැත්තට. දැන් diverge හැම තැනම මේක වෙනවා නේ. හැම තැනම මේ කම්පියුටර් හැම පොයින්ට් එකම මේ වගේ එන මේ වගේ වෙක්ටර් ෆීල්ඩ් එකට කියනවා මොකක්ද solenoid field කියලා. F is called solenoid field whose divergence is always equal to 0 at anywhere in the space. Does this make sense? So this tool is very important, right? So you can find whether there are source or sinks. Yeah, sinkhole and source. Yeah, if you look at this example here, look at this. If you consider this vector field here, if you compute the divergence of this vector field at any point x comma y, right? So what do you get? What do you get? A constant, positive value. So at any point, flowing out than in. ඕනම තැනකදී ඒ කියන්නේ හැම තැනම සෝස් එකක් වගේ නිකන් මෙහෙම විකිරණ එකක් තියලා හයි මොකක් හරි එකෙන් රේඩියන්ට් එක විහිදෙනවා වගේ මේ සෝස් මේ to feel ඇතුළට යනවට වඩා එළියට එනවා දඩබඩ ගාලා vector field එක මේක measurement එකක්. So this is very useful tool to understand about the vector field. Yeah, so if you look at this example, this is another example. Yeah, same example here. So when you compute the divergence of this vector field at anywhere, any point, so always 0. So that means if you consider there is no point source that is producing any vector field. Flowing in, same with flowing out, flowing everywhere. Flowing in, if you have fluid, which is flowing in and the same amount flowing out. මේ වගේ එකක් කියනවා solenoidal vector field එකක්. මොකද හැමතැනම divergence එක 0. Make sense? Any questions? Any doubts? Any questions? Is this a useful tool in vector calculus? This is a very useful tool. Divergence of a vector field. Compressible. Yep, questions? 37, yeah. Divergence. Any questions? Divergence of a line seems to be circular because there's no source at the origin. But here we have positive divergence at anywhere. So therefore we have a source at the origin. There are fair line coming out of that. Questions. Yep. අරේ positive වුණොත් flowing out ගක් වෙනවා ඉන්ට වඩා බින්දු වුණොත් මොකද වෙන්නේ flowing in එකයි out එකයි දෙකම එකයි negative වුණොත් flowing in out වෙනවට වඩා ඇතුළට යනවා ඒක sink එකක් වයි sink hole. Yes, questions? Yep. Doubts? Any questions? Now we are going to talk about curl of a vector field. Curl of a vector field is given by this cross product of gradient operator and the field itself, right? So let's see Yeah, let's try to compute that. Yeah, gradient operator, what is that? So which is a vector operation, a vector operator. First component is partial with respect to x. Second partial with respect to y. Third partial with respect to z. Let's take the cross product. So because these are three-dimensional vectors, you can use the determinant of this matrix would be the cross product. Partial z f g h. The first component, this guy, partial with respect to y minus partial of g with respect to z. That is first component. And the next one, ignore this column and row. Negative, remember this negative sign. This one times this. Okay, partial, then this is way around. H, X. Yeah, other component, this one is, G with respect to X minus, this is normal cross product. Yeah, this is normal cross product, right? Yeah. Partial of G with respect to X minus partial of F with respect to Y. Yeah, F with respect to Y. Normal cross product, right? Yeah. So same thing here. Partial with respect to Y minus G with respect to Z. Yeah. First component, second component, F with respect to Z minus H with respect to X. Yeah. Normal, right? Yeah, same. Okay, normal cross product, right? Because these are three-dimensional vectors. This operator also three-dimensional. So you can take the normal cross product. So this is operator, these are operators. Okay, got it? Yes. So that is the definition. So how do you compute? So now, let's compute, let's compute curl of this vector field. Okay. So what is the curl? Curl of this vector field to understand. First component, let's see, look at x, y, h. Okay, this is h. Yeah, take partial derivative with respect to y. Partial derivative with respect to y. Yeah, so this is, so you can, very easily compute x, 3x, y squared. And minus partial of g, middle one, partial of that one with respect to z, middle one, which one? This is with respect to z, no z terms 0. Yep, no z terms. Like that, you can find the curve, right? First one with respect to z, let's see. First one with respect to z, minus 3z squared. Minus h. Last one with respect to x. Last one with respect to x, this one. plus y cube like that. Yeah. So let's find the last one. Yeah, g, yeah, middle one with respect to x. Middle one with respect to x. Yes. X, yeah, 2y. First one minus first one with respect to y. First one with respect to y, no y here. This is the curl of f. Okay, yeah, very easy to compute the curl. Now we find the meaning of curl. Yeah. So what is this? Curl of a vector field. It measures twisting or circulation of a vector field. So let's see. Yeah, so this is your vector field here. If you drop a stick, say paddle or stick, small stick, let me draw. So like this. The curl gives you, so curl measures the circulation of a vector field. So if you want to find the circulation of this, at a certain point, let's say at the origin, I want to measure the circulation of twisting or circulation of this vector field. මට ඕනේ මේ vector එක ඇඹරෙන measure එක ගන්න. ඇඹරෙන ඇඹරිල්ල measure කරන්න. ඒකට මම මොකද්ද curl එක compute කරන්න ඕනේ. ඒක මේ හැමතැනම මොකක් හරි if I drop a stick like this මේක කොච්චර කැරකෙනවද මෙතනදී මොකද්ද මෙතනදී තමයි මාරට කැරකෙන්නේ. එහෙනම් curl එක origin එකේ මාර වැඩි මෙතෙන්ට සාපේක්ෂව නේ. So actually curl gives you the measurement of a circulation of a vector field. It different at a different point. So at this point the curl is it seems like curl gives you a maximum value at the origin than any other point. The curl is let's find the curl of this vector field here. So what is the vector field? This one. You could find that. It takes time. You can calculate. Actually it is the measurement of the circulation of a vector field. Right, let's carry on. You look at this. Here this same vector field, right? Same circular vector field here. Minus y. The second component is x and the z and 0. Same thing. Okay. So what is the curl of this vector field? Okay, compute that. No, they haven't computed. So you can compute this, right? I don't take time to compute that, right? So if you want to measure the circulation of the vector field at a certain point, so you have to compute the compute the curl. Here look at it, drop a small twig in the leg and twig may be pushed by the car so that it travels in the large circle. The curl will not detect this. Curl of measure is how quickly and in what orientation it's rotating as it moves. එක මෙහෙම කැරකෙනකොට මෙහෙම ෆෝස් එකක් දෙන්න ඕනේ මෙහෙම දෙන්න ඔතකොට තමයි තඩපඩ ගාලා කැරකලා ඒකේ ඩිරෙක්ෂන් එක තියෙන කෙලින්ම උඩට screen එකෙන් උඩට හරිද? The direction, so because this is a vector valued function, this is a vector valued function, right? There's a direction, right? So how do you find the direction? So if let's say, so this is your, yeah, so this is your vector field. Yeah. So if you drop a stick into this vector field, it is yeah, it is rotating in this direction. So you can use your right hand side to find the direction of this curve. Yeah. So yeah, so this vector field is rotating in the direction of, yeah, rotating clockwise. Then if you, yeah, if you use your right hand side and put your set of all fingers, yeah, fingers in this direction, then thumb, your thumb, the direction of thumb gives you the direction of the curve. Yeah, so curve pointing upside, or yeah, popping out from the screen. Yeah, so direction of the, yeah, curl of this vector field is coming out from the screen. Yeah, screen. Yeah, yeah, yeah. As you see here, this one. Yeah, so there's, yeah, so the curl at the origin is much. I think when you compute this, yeah, much, the magnitude of the curl is much bigger than any other point magnitude, right? Yes. All right. So here we go. Here, so here, let's say, here this is a practical problem. So, so this is your paper, right? Take a paper and spread dust iron. So this is the iron dust, right? Spread the iron dust and yeah, set a wire through this paper, right? And apply some current. Then here you will see some rings appearing on this paper here. So these are iron rings. So they, if you apply, yeah, current through this, through this wire in this direction, you can see those, iron dust, yeah, circulating like this. Yeah, not circulating. You will see this pattern. So, so if you, so this is the vector field, and the direction of the curl of this vector field is given by this, the direction of current of this through this wire. Yeah, is given by the current. So did you see the difference? The divergence of a vector field and curl of a vector field. Curl is a vector, while divergence is a scalar function. The curl is a vector valued function, while the divergence is a scalar valued function. So did you see the difference? If you want to measure the circulation of a vector field, you have to compute, curl. So here, look at this. If you have a vector field, right, and whose curl at everywhere is equal to 0, then that vector field, F is called, it's called irrotational vector field. It is called irrotational, not rotational, irrotational, right? So that's why irrotation, not rotating. That field is not rotating, right? So you can compute that. So if the curl of that vector field is 0 at everywhere, right? So then we call that field is not rotating. So කිසිම circle එකක් නැහැ. Irrotational. It is an irrotational vector field. Right? Circle එකක් නැහැ. Twist වෙන්නේ නැහැ. අඹරන්නේ නැහැ. Vector field මේම කෙලින් යනවා. නිකන් මේ වගේ එකක් මෙන්න මේ වගේ එකක්. එතන නම් දැම්මොත් මුකුත් කැරගෙන්නේ නැහැ නේ. මේ හරිය දැම්මොත් නම් මෙහෙම දැම්මොත් පොඩ්ඩක් එනයි මේක බලන්න කම්පියුට් කරලා මේක කම්පියුට් කරලා බලන්න බිඳුවක් එනවා නම් අන්න rotational vector field. Yeah, did you understand today's lesson or any questions? Don't have much time to cover other parts. And so these things, yeah, I will explain these things next week. Yeah, any questions? What are the major topics? After this, I think divergence theory and Stokes theorem. Yeah, divergence theorem, line integral, and there are three theorems, I think. Divergence, Stokes theorem, divergence theorem, and Green's theorem. Yeah, those are the major topics. And we have only 4 days to cover everything. No, yeah, I will give it a try to cover everything. Yeah, so yes, yeah, let me see. Yeah, so here, now we are here. This one, yeah, this is line integral. Line integral, 10th one, Green's theorem. Yeah, 11. Surface integral and divergence theory. And Stokes. Yeah, that's all. Stokes theorem. Yeah. Yeah. Yes. Any questions? Any doubts? Oh, but the I can't exam එකට එනවාද? මොකද්ද directional derivatives වෙනකන් නේ. තෙන්ට වෙනකන් ඕක බලන්න. Directional derivatives. Yes, you have a small test next week. Yeah, Wednesday. I think they conduct 2 sessions. I think yeah, so you can take either one, right? Yeah, I hope this makes sense. Do you have any questions?